Yeah, what's up, guys? Welcome back. Episode 50. It's crazy to say episode 50, not gonna lie. I feel like that's a. Sorry, I had to fix my hair, it was in my eyes. I feel like that's a great milestone. Like episode 50, I didn't think I'd even get to episode 50, to be honest, so I'm really happy about that. Yeah, we're gonna keep going. So, yeah, let's check out our Pokemon of the day for episode 50. We shall listen to the sound. We got a Diglett here. Halfway to 100. Let's go. Diglett dig, Diglett dig, Diglett dig, Diglett. Let's listen one more time. Let's go. Let's go. Okay. We're gonna get into it, so. Ooh. Let's take a look at some. Oh, whoops, not this one. Powerful study program. Let's take a look what we need to finish. Maybe we'll take a look at another binary tree problem. Take a look maybe at a hashing problem. Got some sorting problems here. That's interesting. Maybe we'll take a look at those a little later. But let's take a look at some binary tree problems, and we'll take a look at some hash problems. These definitely gonna take a long time to finish. I mean, bro, with binary tree problems, 65 questions, like, you know. Take a look at find bottom left tree value. Okay. Well, obviously we know that this is DFS here, so let's do our DFS function here. We want to pass in our DFS here, so we want to start the root, right? I think our base case here will be, well, if no dot left, if not no dot left, and not no dot right, I guess we just want to return, right? We want to return our, I guess return our node, right? I mean, we don't need any store, we're only returning one singular node. I think our recursive case in this case would be just to do node is equal to, or we recall our function DFS node dot left. And we just keep going until the thing here. So I think this will work, but I mean, this seems like pretty basic, but I mean, really, we're only going left, so. Otherwise, maybe we return 0. I don't know. No. Why are we returning null here if not no dot left and not no dot right return? What are we missing here? Why are we returning null here? I didn't think about that. So our current base case, I thought we were always going to return the leftmost node here. But in this case, return 7. Interesting. Okay, so I was thinking the total leftmost node. So this is obviously incorrect to begin with. Okay, so now that I think about it here, we're going to have to track obviously the depth here, right? We need a variable for the depth. We're going to pass in, well, 0, right? We're going to have a value for our max depth. We're going to initialize that to -1. And then our left value, which is equal to 0. Cool IDFS function here, and then we turn our left value, right? Now base case here changes, so we do well. If not node, then we just return, right? Because we're returning an empty value. Returning empty value. Alright, so then we want our recursive approach. We're going to have to check, well, if our depth is greater than max. And the max depth, we want our depth, max depth to be equal to depth. Alright. And our left value is equal to no dot left. And obviously we just want to recurse DFS no dot right. We want to pass in our current depth plus 1. Current depth plus 1. Current actions look a variable max depth. I don't think it's going to be able to access left value either. Work. I'm missing something here. No, we're just gonna pass in the variables. Let's just pass in the variables. It's just easier. That max that left val. If not, no, we just return the max depth and our left value. Let's see. Let's take a look at that. Oh, forgot to return our function. To require potential targets. Oh, whoops. Why am I returning 0 here, dude? What am I doing here? No dot val. Okay, we got that. That was an interesting problem. Didn't read the problem description correctly. So here we got our base case. We return an empty value, right? We immediately return our max depth and our left value. So it doesn't get to here and it updates our max depth value. Here we just recursively recursively call our DFS function here with all of our stuff, and then we, with our max depth and our left value, and then we call it out here simply, and we just keep track of the values. I mean, I think it's a pretty straightforward problem. Nice. Let's take a look at a different problem. I'm a little bit not happy with my performance in that one, not gonna lie, but hey, it's alright. At least we learned. Find the largest value in each tree row. That's definitely BFS right there. Let's do a BFS. 1, 3, 9. Oh, my back. Oh, my back. Definitely BFS. I think you can do this using depth first search, but we're going to do it using breadth first search. Oh, wait, we've got... Sorry, we've got to go back to this one here. We want to do our DFS approach, our iterative DFS approach. DFS node. What else do we want to pass in here? I'm thinking maybe our left value. I'm not sure. I don't know. Do we pass in our left value? Do we not? Yeah, let's just do it. While stack our left value. Okay, well, we do while stack, right? And we want to pop from our stack, so we want to do well node. Sorry, this needs to be root. Oh, we don't want a stack, we want a queue. Jeez, dude. Queue. I always forget. Okay, let's import our DQ here. DQ. Then we do DQ. Does that work, dude? I don't know. Left value is not defined. I think that's fine, right? I think we do a while DQ. Root left value is equal to stack.pop. Alright, that should work, I think. Can I actually look where left value is associated with a value? Okay, finally. Okay, we have root. dq.pop, right? So we want to track our max depth, and then we want to track our depth, right? Then we want to do, well, let's actually track this. What we want to track. What do you think here? Okay, we got our max depth, we got our left value, we got our DQ here. Sorry, we want this to be node. I would call it root. Our value DQ root. Our value is max depth -1. Try to think here. How do we implement BFS? I'm actually just not really 100% sure how to implement Iterative BFS. So here we want to check, well, we need to somehow check the level size. I think the way we check the level size, we do the length of length of DQ. Alright. And we do, well, for I in length size. Right. We want to node is equal to dq.pop. Right. So here we're popping the level. Right after we pop the level, we want, well, we want the leftmost node. The leftmost node is always going to be the first one, so we do, well, left value is equal to for I, and we want range, length size, we want, well, we want the, if I is equal to 0, we want left val is equal to node dot val. Then we want to pass in our next thing. So we do, well, do we do this within the for loop though? I think we would do this within the for loop. I think. DFS dot, shit, dude, I don't know the functions though, dude. That's the thing. Is it enqueue or is it append? No, I didn't know this was a double-ended queue in Python. Interesting. Okay, I think this is meant to be pop left though. Where's the pop left? Pop left. Then I think we append dfs.append, because this appends from the right end of the queue. So what? dfs.append node.left, dfs.append node.right. Oh shit. Then we just want to return, well, we want to return our left value. This is probably not going to work, but attribute pop left, is it a capital L? Bro. You know what I forgot here? We have to check, well, if node dot left, if there is a node dot left, then we want to append. If node dot right, then we want to append, right? Oh, it's not DFS. That's why we're not appending anything. DQ. Okay, well, we did this wrong here too. So this is meant to be Q is equal to DQ root. Got length, we're looping through. As equals to node to the left, node to the left. Okay, let's try and run this now. Oh. I need to change this. Okay. We want the length of Q. Let's copy this value because we need to do this here. We need to do this here. Unbound method dq.pop left. Okay, so this needs to be Q. Try that now. Looks like we got an infinite loop. Why do we have an infinite loop? Well, we're not exiting, that's why. Okay, so we need... How do we exit this infinite loop? That's why. We don't have our cube here. Okay, what are we getting here? We're getting 0. Okay. Well, at least it's running now. Well, we're not even updating our left val. We need left value. What do we get here? There we go. Like that dude from Wolf of Wall Street. Okay, what do they do here? They do the iterative way as well. They create a queue, queue.append the root, element is equal to none, while the length of the queue n is equal to the length of the queue, while n is greater than 0. Other queue left, element is equal to node.left. If node.right is not none, queue.append node.right. If node.left is not none, queue.append node.left. Return element. I just got this weird video of Travis Kelce and Taylor Swift. I'm curious how old is Taylor Swift? 35. Travis Kelce age, it must be the same. 35, yeah. Okay. Jeez, they're only 12 years older than me. Damn, bro. Ah, damn. Okay. We did this. So let's get rid of that. Let's find our largest value in our root here. Oh, this is by level. Yeah. Okay. So here we want to find our... Here again, this would be BFS again, right? I mean, we're looking at each value by level, so... yeah. Again, how about we start off with the iterative way here? Considering we know how to import the DQ now. Oh, whoops. Let's import this. Yep. Okay. Let's create our queue. So queue is equal to DQ. We want to put our root in it, right? We want to initialize an array here, right? We're going to do while queue. Right. Side of it, we want to grab the length. So we want to do while our length size is equal to the length of the queue. Right. And we want to do a for loop iterate over it for I in range queue. We want to append, well, what is our largest value here? So I'm trying to think here. How can we do this? How can we keep track of our largest value? Well, How can we keep track of our large value? Because we're going to be looking over the queue. Yes, we want to initialize our large val. Check well. Let's initialize this to -1, because what all number nodes in the tree we tend to fall. Or it could be negative to negative infinity. Okay. So I think we're gonna have to make our largest val and start this as an infinite value, which I think you do this like this or something, right? I don't know. I have to double check. I'm not really 100% sure. A little bit of Stack Overflow. I think this is how you do it, but I'm not 100%. We need negative infinity, I think. How do you do negative infinity though? Oh, I don't know. Trying to think here. Well, you know. Do well. How can we keep track of the largest value here? Let's ask. I'm not sure. Negative infinity. Bro, how do you do it to negative infinity there? I was right. Like, what do you just do? Negative. Okay, float. Oh, okay, I was close. We actually put it in here. Right? Okay, so then we check well. Node is equal to stack dot, sorry, not stack, q dot pop left, right? We pop here, and we check well. If node is larger than large val, then we just want to append here, right? So we just do q dot append. Sorry, not q dot append. We do large val is equal to node dot val. Then we add our left and right. So we would do, well, if node dot left, then q dot append, node dot left. Q dot append, node dot left. Node dot right. Q dot append, node dot right. We want to return our res here, but we need to update our res. Is in the for loop. We need to go outside the for loop. Res dot append large val. Let's see if this works. I think this should work. Collections.dq. Oh, whoops. Need that like size. My bad. Node is greater than large val. This used to be tree node and float. We need this to be. I'm trying to. There we go. Let's run this now. Sweet. Sweet, 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 sweet. Oh. Has no attribute val. Oh, we need a check. Well, I guess we need a first check. Well, if not root, return. Oh! If not root, return. Okay, this should work. Yeah, baby. Yeah. Submit it again, dude. High pipe. Nice. And we did iterative approach. Now we're gonna do a recursive approach. Let's check it out. So how would we start with a recursive approach, right? Definitely think the recursive approaches are harder than the iterative approach, I think, but think about it. Okay, so what are we looking for again, right? We're looking for, so we're gonna need a res array, right? We're going to need a DFS function, or maybe we do a BFS function. I don't think we've done recursive BFS before. I'm trying to think here. How can we do this recursively? Well, okay, let's do. We need our node here, right? So I guess we can do our backtrack function. Sorry, DFS node. All right, and we want to keep track of the largest node at each level. How can we do that? I'm actually not sure, to be completely honest. If we wanted to do DFS, then we have to keep track of the level some way. I'm not sure. I'm not sure how to do this recursively. Let's take a look. So they do tell me that they implement DFS to do this recursively. Not BFS. So we have to think about it. So obviously we're going to have to keep track of, some sort of depth or something. So it's interesting kind of the way they do this, right? So, I mean, I was right. You need to keep track of the depth here. Right, so, I mean, we start off at depth 0 and we pass in our root here. Right, we initialize our res rate here, but let's do it here just for purposes here. We return our res, right? So need our base case here, right? So our base case would be, well, if not node, right? If there's no node, we return, right? If it's null, we return. We need our recursive case, but we got to check each time, well, what's our depth? So how do they do it here? Well, they do, if we reach a new depth, add a new entry in the result list. Depth is equal to length result. Result.append node.val. That's kind of cool what they do here. They use the depth to, you know, create a new entry, but then they update it every time as well, but using the depth as the array here, as the index of the array as well, which is very smart. I wouldn't have thought about that. So here they use, well, if the length of result, so if the length of res is equal to the depth, sorry, if depth is equal to the length of res, maybe we want to pass in 1 here actually, right? Oh no, they pass in 0. Okay. I was thinking we'd want to start at 1, but okay, like the result. Well, let's do what I think. Let's pass in as 1, because that's what I would have done if I wasn't looking at the solution. So if depth is equal to the length of res, what would we want to do here? Well, result.append node.val. Why do we append here though? Result.append node.val. And then they use the else here to update. See here, they use depth as the index, and then they do a max function, and they do, well, we look at the current val, so node.val. Sorry, I guess result depth, and we look at the current val, node.val. Right. And then obviously we append here. We do dfs node.left depth plus 1, dfs node.right. Depth plus depth plus 1. But I just don't understand why we're checking here if depth is equal to length res. Let's run it. I mean, it's going to be incorrect because you got a 1 here, but oops. How does this work, dude? I am so confused. Let's get up our paint here and go through this code ourselves. We can use this example here. All right. Do 1, 3, 2, 5, 3, 9. Okay. That was probably a little bit too big. It's okay. Can we make this a little bigger? Okay, there we go. Alright. Okay. So let's run through this code. So we pass in our root first with a depth of 0, right? So this is 0 here. If the depth is equal to the length of res, we append no.val. So we append 1 to our array. Alright. And then we do, well, DFS no.left, depth plus 1, DFS no.right, depth plus 1. Let's do our stack here so we can see our calls. So we append, we do, well, DFS no.left, right? So we keep track. This one, so we do no.left, we go to this value here, right? We check, well, 3, 3, if depth is equal to length res, so our length is 1 now, which is true, then we append, so we're appending 3. And then we go no.left again, right? Then we append, we look at 5, well, that's equal to the same, so we append 5. Then we do no.left, and we see, well, if not node, we return. So we return the node.left here, then we check, well, node.right, and we return that as well. So then we return 5 in this case. We go back to 3, and we return, well, we do our node.right from before, and we check 3. Well, 3... if depth is equal to length res, then we check, well, res depth is equal to max res depth. They're the same, so we leave it. Then we return this one and go back to 1. We check the right. Well, does 2, since is equal to if depth is equal to the length res, it's not. So we check, well, we do the max here. We see that, 3 is greater, then we move, right? Then we check 9. Well, we do no.left, technically. We see there's nothing there, so we return that. Then we go to no.right, and we check, well, 9 is 9. The max of res.depth is 9. The max here. So, no, it's not. Oh, no, it is, sorry. What am I talking about? So then we update our 5 here, and we make it 9. I think that should return 139. Okay, so now I understand what this is doing. So this is pretty much the case where, we haven't, this is our first value, right? And then pretty much every single other time we're going to check, well, is it that? Because in DFS we're going to shoot all the way down to the left. So, okay. I understand that. I really have to go to the bathroom. So I think we're going to do one more problem. We're going to do a hash map problem. Hopefully something easy. How many numbers are smaller than the current number? Okay, let's do this. Let's try and finish off with something simple. An easy problem. Given the array nums for each nums I, find out how many numbers in the array are smaller than it. That is, if each nums I, you have to count the number of valid j's such that j does not equal I and nums j is less than nums I. Interesting. Well, I think we can do do this the way that we did Tucson. We can do a double for loop here. Alright, let's see if this actually passes. Like, Ryan range length nums, right? For j in range I plus 1 length nums. I'm going to check, well, if I does not equal j, and nums j is less than nums I, what are we outputting here? We're creating a list here, so we need a res array. Guess we can do res.append. I'm confused here. Given an array nums, for each nums I, find out how many numbers are smaller than it. Oh, okay. So we look at 8, we see that there's 4 numbers that are smaller than it. J does not equal I. Let's do this. Maybe we initialize it with all zeros. So we can do 0 times the length of nums, because we're always returning the same size. So we can do, well, res I plus or equal to 1. We return res. I don't know if this will work, but well, how does this work here? Oh, we gotta do the ones behind it as well. We need to be circular, so what do we do here? Maybe we don't need this here. Okay, there we go. Let's submit. Yes, it will. Nice. The slowest solution possible. Let's go. Let's try and optimize this a little bit. How can we optimize it? We need, well, I mean, it was to sort the array, so let's sort it. Sort. Does that make a difference in the complexity if we sort it? I'm curious. Like, okay, well, it doesn't work if you sort it like that, because we'd have to reverse from the other side. So maybe we'd have to loop, well, I'm thinking, well, how can we do this? Could we just loop from the other way? Like, we can sort the array and then get the answer for each array element. Look at this guy's solution, bro. Like, this guy really wanted to do it in all van. Like, how many numbers are smaller than the current number? Use the sorted array to find how many numbers are smaller than each element by checking its position in the sorted array. Since sorting takes O of n log n time and we loop through the list once we get the results, this approach is efficient. We create... Okay, so here we do a num.sol. We create a hash or a dictionary. Right? We loop over for I and num and enumerate us in our nums. So we want to take the index and the actual value. We want to do, well, if num not in num too small a count. If num not in my underscore dictionary, then we want to do, well, my underscore dictionary num is equal to I. So our key is our actual number, and our I is our index. Okay. I don't really understand right now. Oh, okay. Right, so we return, well, a list. Minus score dick. Okay, so what we're doing here is we're creating a dictionary, we're storing the actual index inside of our hash map here, right? So every value before it would be considered smaller. So if we do a new here, we can kind of visualize it here. So what do we have here? We have 8, oh my gosh, dude. 8, 1, 2, 2, 3, right? And we do, well, we have our dictionary here. So this is our dictionary. We map each value here, right? So we sort it first. So let's print out. I guess we can just sort it ourselves. That's all right. Okay, so we start off with 1, right? So we're doing this in a sorted array. So 1 would map to index 0, right? And 2 would map to index 1. If num not in my dictionary equal to I. I'm confused here. What would we be if we have a duplicate in my dictionary? Okay, we don't even, yeah, that's what I thought. Okay. 2, 1, 3, 3, 3, 3, 8, 4. That's our dictionary here, right? Geez, bro, I'm reversing it. Alright. Yeah, it doesn't work. Does it go like this? Is that how we do it? I don't think we need to. I need to go to the bathroom. Why is this reversed? I'm curious. Like, did I sort it the wrong way? Why is this reversed? I think it's the sorting. I think maybe. Yeah, that's what I thought. When you sort the array and store the index of the first occurrence of each number in the dictionary, you capture the number of elements smaller than each number. However, the list you are processing numbers is still in the original order, and the dictionary is built using the sorted array. Okay. What's going on? Okay. Yeah, we're sorting it the other way. That's why. Okay. 8, 0, 1. 2, 2, 3, 4. Oh. Let's print out. I don't know why it's so tough for me to visualize this right now, but I mean. Okay, so we sort our array. Like, oh my gosh, we were right, bro. What am I doing? Well, 1, 0, 2 is 1, 3 is 3, 8 is 4. Okay. So we do that. We sort it. We do that. Now we return a list here from myDicNum for num in nums. so I did num for num in nums. So if we have, in this case, we have our sorted array now, which is 1, 2, 2, 3, 8. Right? So this is our sorted array. So we have 1, there's 0 less in it. We have 2, there's 1 less in it. We have 3, there's 3 less in it. We have 8, there's 4 numbers less than it. Right? This also skips over the duplicates here, so j does not equal I. We don't want the duplicates, right? So then we just return, well, the numbers in our dictionary. So then that's why we loop over here. We do mydict num for num in nums. So we're looking for after each I in nums. So we're looping over the original array, which is here. So we loop over 8, we return 4, we loop over 1, we return 0. Yeah, we loop over 2, we return 1, we loop over 2, we return 1, we loop over 3, we return 3, because we're storing how many numbers less than it. Okay, well, that makes sense now. Which I think, I believe this is a O of N solution, which should be the fastest solution as well. Yeah, okay. Okay, all right. We're going to leave it there. Appreciate you guys watching, and I will see you tomorrow.